Hey, what's up, guys? Previously, I introduced the Fourier transformation of Boolean function. But I think I want to say about some basic property of the Hamming space, and this is a very simple idea. So I think it's worth to spend a little bit of time discussing what is Hamming space mean. Okay, so previously the Boolean function, right, is defined to be 0, 1 to the n. So this is a 0, 1 string with length n mapped to -1, 1. And I introduced say that you can write a Fourier transformation such that using a character if you like group representation. Okay, so I also use this notation as a 0, 1 to n. So this is called Hamming space. Okay, so or simply you can write as f2 to the n. Okay, or basically it's a z mod 2z to n if you're like a more mathematical perspective. Okay, and yeah, let me just introduce why this is called Hamming space. Okay, the simple reason is that we can say something about we can define a distance. Okay, so let me just define a distance. Let's say dxy, right? For every xy belongs to this Hamming space, I can count how many what's the maximum bit difference. So it's maximum of so it's not maximum, it's the number of the bit difference. So it's number of I such that the xi different from yi. Okay, so for example 0, 1, 0, 1, 0, 0, the distance is 3 because of the distance is 2, right? Because the first one and second one are different. And then let's say, and for example, this is 1. Okay, so it's a very simple exercise to check that this distance is actually a metric space. So this is distance, and this xn will become a metric space. Okay, so this is called Hamming space. And then we can define a ball. So we can define a ball, right? We can define a ball. We can define a ball in a Hamming space. Okay, so for example, I can define S of t, which is x belongs to x of n bit string, such that the known of x. Okay, so let me define known. So known is the distance with x0. Okay, so such that known is equals to t. Okay, now I can also define a b of t, which is a ball, such that this is a sphere. This is a ball, such that x belongs to x to n, and x is less or equal to t. Let me just clear this. Okay, and now we can count the cardinality of S of t, right? So this is very simple, right? This is just n choose t, right? Because you change n choose t, so that means you get the t once. Okay, and then this is the summation of n choose I for I from 0 to t. Okay, so this is simple, right? But the goal is to find there's a goal is to find the asymptotics of, let's say, b of t. If you choose let's say if I choose let's say t is comparable to n, let's say t is tau n, so I want to know the asymptotics of b of t's. Okay, so basically I want to know the following. I want to know the following. Okay, so this is, I want to know the order of the following. This is property that or a number that we will use. Okay, so let's start to do something. Okay, so the interest idea is that there is a binary entropy function. Okay, which defined to be h of tau. minus tau log to tau minus 1 minus tau log to 1 minus tau. Okay, so let's say tau is from 0 and 1. Okay, and you can plot it. This is not difficult, I think. Right, so tau is 0 and 1, and when tau equals to half, they become long 2, and so you can prove this. Okay, and the theorem that I want to say is that this theorem is that let tau less than half, then we can count b tau of n, which is a previous, which I just used n times tau, is less or equal to 2 to the n h of tau, and greater or equal to 2 to the n h of tau divided by square root of a pi tau 1 minus tau. Okay, so this is a theorem. So basically what I'm saying is that the volume of the Hamming space for tau of n is bounded by 2 to the n tau, and less or equal to 2 to the n tau divided by square root of a pi tau 1 minus tau. Okay, so this is the interesting thing that I want to compute. Okay, so let's go to a proof. Hopefully it's not difficult. Okay, so let's prove the upper bound. Okay, so idea is that let's say 1, I can write 1 equals to tau plus 1 minus tau to the power of n, and I use the binomial coefficient. So n choose I, tau choose tau to I, 1 minus tau, n minus I. So I from 0 to n, which is greater than equal to, let's say I choose I equals 0 and I up to tau to n. So n choose I, tau to I, 1 minus tau, n minus I. Okay. Okay, so interesting thing is that our I from 0 to tau to n, and the tau is less than half. So you can see the largest term in this is 1, right? When I equals 0, you get when I equals 0, you get tau 1 minus tau. Okay. So when I equals 1, you get tau 1 minus. So let me just write down. So when I equals to 0, you get tau 0 1 minus tau n. When I equals to 1, you get tau 1 minus tau minus 1. When I equals to 2, you get tau squared 1 minus tau n minus 2. Okay, you can easily check that these are greater, this greater than this, greater than this. Okay, you can check by yourself. This is not difficult because their ratio is tau. Their ratio, let's say I divide this, is 1 minus tau divided by tau. Right? But tau is less than half, so this guy is greater than 1. Okay, so that means I can replace this tau to the I to be use the tau n. Okay, so I can just replace I to be tau n. Let's say this is fixed I, and I replace tau n 1 minus tau minus tau n. Okay, so very simple exercise is to write this guy as a summation I from 0 tau n choose I 1 minus tau n tau divided by 1 minus tau n. Okay, so which means that 1 is greater or equal to, let me just copy. So I from 0 n choose I 1 minus tau n tau minus tau tau n. Okay, so final easy exercise to check the following. Let's say 1 minus tau n, 1 minus tau, which is this one, and the tau n is actually, you can 2 to the minus n minus tau log 2 tau minus 1 minus tau log 2 1 minus tau. Okay, this is not difficult. So it's a 2 to the minus n h of tau. Okay, so that means 1 greater or equal to 2 minus n times h of tau times this b of tau n. So which means that this is volume. So which means that the b of tau n is bounded above by 2 to the n of h of tau. Oh, difficult. Okay, so let's do in the lower bound. So this is the upper bound. So we already proved the upper bounds. Let's go to the lower bounds. Okay, so lower bound is using a Stirling formula. So there's a formula that I will not prove in here, but it should not be difficult. Okay, if you want to see my Stirling formula proof, that I will post below that you can use. You can use the integral representation over the basic 1 over n and do a summation. Okay, and I will post the link below if you want to see a proof. But n factorial is greater than square root of 2 pi n and n plus half exponential negative n. Sorry, exponential n. Okay, so so this is different from original Stirling formula, right? The original Stirling formula looks like this, but actually there's this is more precise one. Okay, and actually you got the greater. Okay, so this is the precise one, and you can do exactly the same calculation. Okay, so you can prove that the n tau n, if you just expand it, let's do this. So n factorial tau n factorial minus tau n factorial, and then you just use this. Okay, and you can prove this is greater or equal to 1 divided by square root of a pi tau 1 minus tau 2 to the nh of tau. Okay, so which means that the summation of n choose I from 0 to tau n is basically greater or equal to n of tau n. Okay, so obviously, right, because every term is positive. Okay, so we should prove that b of tau n is greater than or equal to 1 over square root of 2 pi tau 1 minus tau. Okay, this is a Hamming space. Okay, and finally, I want to say something. I want to say a definition, which is called a linear. Basically, it's an error correction code. So there's a binary linear code. So basically, this is error correcting codes. I'm not expert of it, but I like the mathematics. So I think I have a right to write fill whatever I want. The binary Hamming codes. So idea is that this is also a definition. Now I just want to say a definition. Definition is that so you consider f2 to the n. Okay, and then you consider C is a subspace of f2 to the n. And what you're saying is that let's say dimension C is K. Okay, so you take the K-dimensional subspace in the n-dimensional F2 to the n, and the dimension is K. So in order to represent of this, right, you can write C as this is a code. This is a code. Okay, so basically you can write a K-dimensional vector, right, as a basis. Okay, so it has a basis. Let's say x1, x2 up to xk. Okay, and each xi is f2 to the n. Okay, and then we can define distance of the code defined to be the maximum, right? So the maximum of the Hamming distance. There's a d-Hamming with the code in it. So basically it's xi, xj, where I different from j. Okay, so in a notation that people will write this as a code. So this is a linear code. So basically binary code is just a subspace, which is just the pair that nkd that you choose. I mean, C is a subspace of f2 to n. Okay, so since it's a linear space, right? So you can find a parity check matrix. Okay, such that so basically simply speaking, that there is h of t, such that x h of t is 0. Where x belongs to C. Okay, so this is definition. I mean, you can find that kind of H because this is a linear subspace, right? So you can form this and find the kernel. Okay, so it's just a definition. Okay, I think this is enough for today, and see you guys. So next time I will go back to the Fourier transformation.